Y24 Four-Momentum and E equals mc squared. So what we learned in the previous class is for the full vector. The full vector, especially for displacement x mu, is c tau 0 if a particle is at rest. And we used the Greek letter that represent the four components. The zeroth component is time. First, second, and third Cartesian components is represented by these three spatial coordinates. If a particle is moving with velocity v, then the time is not proper time. Instead, it is ct and vt. And this time t is gamma tau, where gamma is 1 over square root 1 minus beta squared, and beta equals v over c. In addition, the square of this four displacement, that is sometimes written like that, is zeroth component square subtracted by spatial component square, the usual Euclidean square. However, we need to put the negative sign for the components for the spatial component. Okay, so this is the invariant quantity on the Lorentz boost. We are looking for any full vector that follows the transformation rule the same as the space-time coordinate code for displacement. So we have a matrix lambda that is a 4x4 matrix, and we make use of this relation to any one that satisfies the same transformation rule called Lorentz transformation. This x or other four vectors satisfying this relation is called Lorentz covariant. Covariant means it varies, its component varies systematically, satisfying the Lorentz transformation. Sometimes a physical quantity is invariant, that does not change. So invariant scalar, something like this x squared, any scalar product expressed in such a manner. Speed of light is invariant on the Lorentz transformation. That is the beginning of the beginning assumption that is called the postulate of special theory of relativity. In addition, invariant quantities are proper time, that is the time measured in the rest frame of the particle, and proper length, length measured in the rest frame of an object, rest mass, mass measured in the rest frame of an object. All of these are Lorentz scalars that does not transform at all. First of all, we review for displacement. We usually put Greek letter mu runs from 0 to 3. So we put upper index instead of lower index in here. Lorentz transformation is for the transformation of these four displacement. So x prime 0, x prime 1, x prime 2, x prime 3, this can be obtained by substituting this matrix and x0, x1, x2, x3. multiplication of this matrix will result in the four components of the four displacement in any inertial reference frame. As we already studied, the scalar product of a four vector that is defined in not in a Euclidean space, but in a Minkowski space, has a metric of the form, therefore, square of this four displacement that is at rest frame C tau 0, 0, 0, and the moving frame CT V1T, V2T, V3T, that are components of the Cartesian components of the velocity, something like that. So when we square this in a frame and in another frame, regardless of the frame, the square of this Lorentz four vector for displacement is invariant, that is C tau squared, where tau is the proper time. If x is a four vector, and we have a coefficient that are Lorentz invariant, something like tau, m0, l0, something like that, they are all Lorentz invariant scalars, then this linear combination of Lorentz four vectors also satisfy the same transformation rule on the Lorentz boost. Therefore, the shift in the coordinates in any inertial reference frame can be converted to another frame in such a manner. Therefore, the first application of the four vector other than the four displacement can be made by taking the partial derivative with respect to not time but proper time, that is Lorentz invariant quantity. Only if the coefficient is Lorentz invariant, we can still make use of the same transformation matrix called Lorentz boost matrix. Therefore, the four velocity is not defined by the time derivative of t. Instead, it is the time derivative of proper time. Here, velocity is not a full vector. Let's see. This one, x mu, that is either c tau 0 in the rest frame or in a moving frame. Why don't we compute the proper time derivative? Use this. You will find, because the t equals gamma tau, this tau disappears, and this is for velocity. Why don't we square this time component squared, spatial component squared? You will find gamma squared equals 1 over 1 minus the beta squared. So this guy is always 1. So it is invariant. So this four velocity has the scalar product of with itself that is the same as the speed of light squared, and this is true for any four vector. Four vector square must be Lorentz invariant. That's fine. We can make use of this, still the same value, that is a c squared. However, if I take the derivative with respect to time, t equals gamma tau, so this relation is not satisfied anymore. For example, dx mu time derivative, it is cv. And when you square this, c squared minus v squared, aha, this is not invariant. Why? In the rest frame, it is a c squared. In the moving frame, they are different. Aha. So this is not a Lorentz four vector. So this is this four velocity, that is the time, not time derivative, proper time derivative of a four displacement, that is four velocity and four vector. For momentum, because we have constructed the four velocity, we multiply mass. This mass must be Lorentz invariant. That is the rest mass. Rest mass multiplied by the full velocity is the four momentum. Why don't we square this? Square of this four momentum gives m0c squared. Why? Because u squared equals c squared. What you have done with p mu equals m0 multiplied by u mu. Because u mu squared is c squared, the answer is just nothing but m0c squared. Okay. So we have constructed a four momentum that has a time component gamma m0c and the spatial component gamma m0v. Okay, let's substitute gamma. Then the spatial component of full momentum shows that we have rest mass multiplied by the velocity. This is the linear momentum of Newtonian linear momentum. We have additional factor that is gamma. We can interpret this product of gamma and rest mass is the mass of a particle. And we find that the mass of particle depends on the velocity, and as it reaches the speed of light, the mass of a particle can be increased to an arbitrarily large number. That's the reason why whatever energy used support for the acceleration of a particle, it cannot exceed the speed of light because the mass becomes arbitrarily heavy. Okay, what we have found is that mass seems to be increasing depending on the velocity. Well, why don't we compute the force, ordinary force, that is the time derivative of a force. This force is not a four vector. This is the spatial component of a four vector, and we take the usual ordinary time derivative. Then the expression for the momentum is like that. We substitute this in here to find that time derivative of spatial component of the four momentum is like that. We can find that if I rewrite this one, multiply both sides by dt, then because this one is a constant, dp over m0c is the total differential of beta, where beta equals v over c. Why don't we compute the kinetic energy in relativity? Kinetic energy is the work done by an external force to accelerate a particle from at rest to a state that is moving with the velocity v. That can be done by making use of Coriolis work kinetic energy theorem, just like what we have done with the non-relativistic case. So force times displacement. Force is dp over dt. Now this dt is moved to in here by changing variable from position to velocity. Okay, this is the definition of the velocity. All right. And we remember that beta equals v over c. Therefore, v is replaced with beta times c. Now, dp in the previous page, dp is expressed in terms like that. So we substitute dp in here. Finally, it is expressed in this way. So energy, kinetic energy, divided by a constant that is m0c squared is this integral. We can make use of integration by parts. So this is something, some vector times this. So this is a total differential of a scalar product subtracted by b dot dA, something like that. So integration by parts can be applied in here to have this expression. Now we know this is differential of beta squared, right? And that is minus 1 minus beta squared, the total differential. So this one. Oh, what's that? This is a dx, something like 1 over x, something like that. What's that? This is a square root derivative. Therefore, we have completed this integral from the rest v equals 0 to a state with a constant value, finite value of velocity. As a result, simple algebra will lead to this result. You are familiar with this vector. This one is gamma minus 1. As a result, Einstein has found that the kinetic energy of a relativistic particle, that is the work done by an external force from rest to a state with the velocity v, is m0c squared multiplied by this Lorentz factor gamma minus 1. So what happens? Kinetic energy. So kinetic energy is m0c squared gamma minus 1. That means m0c squared gamma equals m0c squared plus t. When a particle does not move, kinetic energy disappears because gamma equals 1. Even if kinetic energy vanishes, still this one is not 0. We identify this value, gamma 0c squared, that appears here. The zeroth component of the four momentum is actually m0 gamma c squared divided by speed of light. And we remember this is mv, that is the momentum, while m has the velocity dependent factor. In here, this is the energy of a particle, that is a sum of rest energy plus kinetic energy. Even if a particle is not moving at all, Newton's theory does not have any intrinsic energy of a particle. However, Einstein's theory of relativity shows that any object that has non-vanishing rest mass must have intrinsic energy called m0c squared. And if this mass disappears, we have a tremendous amount of energy that is usually used in the atomic bomb of atomic power plant. As a result, for momentum has a momentum component that has a mass dependence, the velocity dependent mass, and zeroth component of the form momentum is now identified by the energy. And the energy is sum of rest energy and the kinetic energy. So because of this, when the mass disappears, a huge amount of energy can be made. For example, we have, if a particle of rest mass disappears, we have m0c squared, a large amount of energy to go. Electron is a very tiny object. However, it has energy. That amount of energy is rest energy of the electron. We can create a particle of mass capital M at rest by converting an energy equivalent to the rest energy of particle. For example, this is a collider. For example, electron-positron. Positron is an antiparticle of electron that has a positive charge and mass, rest mass is equal to that of the electron. We can make a head-on collision, plus minus head-on collision with the opposite direction. Then the sum is energy, and the spatial component of momentum disappears. When electron and positron collide at the center of mass frame, this energy can create a particle at rest. We can increase the momentum of the electron arbitrarily large. At some point, there is a resonance of a particle. So this particle accelerator have created so many interesting fundamental particles like Higgs. Relativistic right triangle is reviewed. Previously, we identified CT, VT, C tau. This opposite side is invariant. If we interpret this one with energy and momentum, then this is invariant. Rest energy divided m0c squared divided by the speed of light. And this side, the mass times velocity. So linear momentum's magnitude will be in here. And the hypotenuse will be energy divided by the speed of light. Okay, so we can make use of Four momentum to rewrite the boost matrix for the Lorentz transformation. We remember it can be expressed in terms of gamma, 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 beta, gamma, beta. Because every component of the Four momentum in here, gamma equals energy divided by m0c squared, we know from this is obtained. This one comes from the energy momentum relation. As a result, gamma, beta, and beta gamma can be computed using this simple relation. So Lorentz boost matrix can always be expressed in terms of Four momentum and energy, spatial component of a Four momentum and energy of a particle.